All right, in this example here, we have a spring. So that should tell you right away what equation we're going to use. It's stretched 0.56 meters and has 130 joules of elastic potential energy. All right, so right away we need to identify this as going to be the displacement, the distance that the string is stretched. This is going to be making this whole thing. This is going to be our PE, elastic potential energy, and obviously we are trying to identify K. Okay, now if it's not obvious, because we're dealing with a spring, we're going to end up using the elastic potential energy equation, where PE is equal to 1/2 kd squared. All right. Now we are trying to find K, so we could rearrange this whole equation to solve for K by itself, but we're just starting out. So let's just start plugging in our numbers that we have and see what happens. So 130 joules is equal to 1/2 K, we don't know K, times the displacement or distance, if you want to think of it that way for now, 56 meters, and we can't forget to square it. Many problems have come for not squaring that thing. So we want to get this K by itself, but we have a lot of numbers we can work with here. And what I'm going to do is I'm going to take nothing I could do on the left-hand side. I'm going to leave this half alone, but I'm going to square this 0.56, the displacement. So 0.56 squared, that gives me width. I'm not going to round until the end. I'm just going to write everything down. So 0.316, I messed that up, 3136. And that's going to be meters squared, just to keep track of our units, multiplied still by K. So once again, I'm writing a lot of things down, but it's the process, and it's going to make sure I don't mess things up like I almost just did. So I'm going to multiply that by 1/2 or 0.5, whatever you prefer. It's the same thing. And I'm going to end up with 0.1568 meters squared times K as the cleaned up version on here. Now I want to get K by itself, and since we are multiplying, I have to, in order to get these separated, I can't subtract. I have to do the opposite of multiplication, or the inverse of that, which is to divide. So I'm going to take 0.1568 meters squared, and that's going to cancel that out because it's divided by itself. But whatever I do to one side, I have to do to the other side. So I'm going to take 0.1568 meters squared over here. That's still supposed to be just a 1. Yeah, I've made it worse, but you're following along, so you should be okay. So I'm going to take 130 divided by 0.1568, and it turns out my K value is going to be 829. We could just round it to 0.1. And the units end up being newtons per meter. It's not very apparent here, but something happens with those joules, which is a big hodgepodge of other units. It's what we call a derived unit. It's a big mix of other units. And so one of those meters is just going to cancel out from there, leaving us with newtons per meter. Anyway, that's our answer. So that's it. That's how you do it. So put a box around it. So let's scroll down a little bit here, and we now have a spring with a K value of, I'll just scooch that a little bit more, a K value of 250 newtons per meter. So that's going to be our K. Right away, we could just identify this. 9,500 joules of elastic potential energy, EPE, if you want to call it that way, or as we've been calling it in our equation, PEE, elastic potential energy. We want to know how far was the spring stretched. That's going to be our displacement, our distance, if you're thinking of it that way, but it's displacement. How far is it from where it was resting at? So because we're dealing with springs, we're going to end up with using the equation PEE is equal to 1/2 kd squared again. Okay, now you could rearrange this ahead of time to solve for distance, but we're just starting out a little bit, and so we're going to plug in the numbers and solve for the variable that's unsolved. We know that PEE is 9,500 joules put our comma there if we want. And that's equal to 1/2 times K, which we do know is 250 newtons per meter. And that is going to be multiplied by our distance squared. And that's going to cause a little bit of trouble in a minute, but nothing we can't handle. Okay, so I'm going to clean things up a little bit. I've got 9,500 joules. Can't do anything with that. Half of 250, I believe, is 125, but it's always nice. It's always a good idea just to double check yourself on a calculator. So 250 times 0.5, and I was right, 125. Okay, that's the part where you're going to make a mistake, where you think you know the answer and you just go with it. But really, you should just double check everything. And that's going to leave us with 125 newtons per meter times the displacement squared. Okay, now here we're multiplying. We're not going to do anything with the square yet because it's just a displacement that's squared. We're not squaring anything else. So I want to get this displacement, I want to get this variable by itself. And since we're multiplying right here, we're going to have to do the opposite of that, or the inverse of that. And we're going to divide 125 newtons per meter over here. And that'll cancel that out nicely, leave us with the displacement squared. But whatever we do to one side, we have to do to the other side. So I'm going to divide over here as well. So I'm going to take 9,500 divided by 125. And that leaves me with 76. And it's going to be joules per newtons meter. It's going to be a whole crazy mess. And, you know, again, do with it what you can at this point. We're just starting out, so it'll come to you. In the end, though, we're going to get this d squared. Is that not the end? Okay, it might sometimes seem like it, but we got to deal with the square. And how do you undo a square? What's the opposite or the inverse of a square? Well, a square root, okay? So we're going to have to square root both sides. So the square root of 76 is going to leave me with 8.7. Okay, 8.7, and it's going to be distance. So what's going to end up happening, or displacement, is all those units are going to get unsquared and cancel out and leave us with 8.7 meters.